Welcome back, class. In today's video, we're going to focus on drawing Lewis structures for covalent molecules and some of the ideas that go along with that. So let's start with a basic process that we're going to go through. And so as we go through, the first thing that we want to do is we want to be able to draw out the basic skeletal structure of the molecule. And so we're going to use some chemical intuition and some rules to help us get to the right skeletal structure. So the first thing is that hydrogen atoms will always be terminal because they can only ever bond once, and so they will tend to be on the outside, or what we call terminal positions of a structure. Using our idea of electronegativity, right? We will place the more electronegative atom on the terminal positions. In other words, we'll have the lowest electronegative atom, or the one furthest to the left on the periodic table, will go in the center of the molecule. Okay, so once we get a skeletal structure, then we're going to calculate the total number of electrons that can be in our Lewis structure. And this is going to involve adding up all the valence electrons for the atoms involved in our molecule. And then we're going to distribute those electrons, with our goal being to satisfy the octet or duets for hydrogen of all the atoms in our molecule. Now we're going to start this by looking at the terminal atoms first. We're going to try to give them an octet. Then, if we can, we're going to go to the central atom and give it enough electrons to have an octet. Now, of course, through all this, we're restricted by having a maximum number of electrons that can be in our structure, right? We have an exact number that has to be there. That's how many need to be there. Now, oftentimes, we'll place them, follow these rules. Everything will have an octet, and everything will be happy. Other times, we may not have enough electrons to give all the atoms an octet. And this is where we invoke multiple bonding, right? Now, the key here is we don't want to just give multiple bonds to give multiple bonds, right? We only want to use them when they are necessary to satisfy the octet, okay? So we don't want to be having lots and lots of multiple bonds if we don't need them, right? That's why we put them in last. Okay, so enough talk of the rules. Let's just draw some structures. Okay, so let's start here with something reasonably simple. So we're going to do SBr2, right, as our initial structure. So first thing we're going to do is we're going to try to draw out our skeletal structure. Now, what's going to go into our skeletal structure? How do we put it together? Well, I said we're going to put hydrogen on the outside. We're going to put the lowest electronegative atom in the middle. So if we look at these, we compare sulfur, which has an electronegativity of 2.5, and we have bromine, which has an electronegativity of 2.8. So it makes sense to put sulfur in the middle. Now, another idea that we can use is asymmetry, right? So a lot of times we'll get into a situation where we have one of a molecule or one of an atom and multiple of another atom, and almost always that lone atom is going to go in the middle and going to be surrounded by the atom that we have multiples of. But those are some ways that we can get our correct structure. So based on this, we're going to put sulfur in the middle. So we're going to have our bromine, our sulfur, and our bromine. I'm going to draw it like this. So now we're going to add up our electrons. So sulfur, being in group 6, is going to have 6. Bromine, being in group 7, is going to have 7. We have 2 of them. So we have a total of 6 plus 14, or a total of 20 electrons that are going to go in our structure. Okay, so when we do that, the first thing, of course, that we do is we have to make bonds. Right? So we have to put single covalent bonds in between the two atoms. Now, I like to do electron bookkeeping to keep track of what I do along the way. So I have 16 electrons left. Now, I'm going to now start to put in the electron as lone pairs, satisfying octets, starting with the terminal atoms. So if I look at my terminal atoms, bromine, they each need 6 more electrons. So we have 2 from the bond, and we need 6 more. So if I need 6 here and 6 here, I'm going to need a total of 12. I have enough, so I'm just going to go ahead and put those in as my lone pair dots. And so we've used 12 more to do that, leaving me with 4. Okay, so I finished with the terminal atoms. Now I move to the central atom, sulfur, and I see that sulfur has 4 electrons around it. So it has 2 from each bond, right? So it has 2 here from this bond and 2 here from this bond. So it needs 4 more. I have 4 more to give it, so I can just put these in here. So that uses up the last of my electrons, so I should have exactly 20 electrons in my structure, which if you count them up, you do, and everything should have an octet. So each bromine has 8 around it, and each sulfur in the sulfur has 8 around it, 2 lone pair, 2 bonding pair. So we have a nice Lewis structure here by applying our system. Okay. So let's do one more that's relatively straightforward here. So let's look at PCl3. So again, do our structure, but the lowest electronegative atom in the middle, that's going to be P. So we're going to place the P here. We're going to surround it by a chlorine on 3 sides. We're going to add up our electrons. So phosphorus, being in group 5, has 5 electrons. Each of the chlorines, being group 7, has 7. So I'm going to put 5 plus 3 times 7. So we have 5 plus 21, 26 electrons. Okay, so I'm going to start by putting single covalent bonds here. So to make 3 bonds, that's going to cost me 6 electrons. So I have 20 left. And now I'm going to start using lone pairs to satisfy octets, starting with my terminal atoms. So I got 3 chlorines that are terminal. Each one is going to need 6 because it already has 2 from the bond. So it's going to be 6, 12, 18. Okay, so we have 18. So I'm going to go ahead and put those in. So used up an additional 18 electrons, 2 more. So done with the terminal, go to the center, and we'll see that phosphorus has 6, right? 2 from this bond, 2 from this bond, 2 from this bond. So it needs 2 more. I have 2 more to give it. So I'm just going to put those electrons in, and now look back, and I have 8 on my chlorine. I have 8 now around my phosphorus. I have a good Lewis structure. And so here's 2 sort of pretty basic structures to give us a good starting point. Okay, let's do a couple more. So let's do, here, let me get my drawing back. Let's get H2CO. So we'll get some that have a few, more than 2 different atoms in there. So what are we going to put in the center? Well, hydrogen has the lowest electronegativity, but of course hydrogen cannot go in the center. So between carbon and oxygen, carbon has to go in the center. So we're going to put carbon, and we're going to surround it by the other atoms. So I'm going to surround it by an oxygen and my hydrogens, like that. So how many electrons? Well, I have 1 from hydrogen, so I get 2 times 1, plus 4 from carbon, plus 6 from oxygen. So I got 6, 10, 12 electrons. So again, I'm going to start by making my bonds, single bonds. 3 of those cost me 6 electrons. Now, I start again using lone pairs to satisfy octets. Now, hydrogen, of course, is done, right? Because it has its duet, so it doesn't want any more. So we'll move on to oxygen. Oxygen needs 6 more. So I'm going to put 6 in here for the oxygen because I have them. That's, of course, going to use up all 12 electrons are now my structure. So I go into the center, I look at carbon, and I see, does it have an octet? Oh, it doesn't, right? It only has 6 electrons. 2 from each of the bonds. Well, how do we do this? Well, remember, if we do not have enough electrons to satisfy everything with lone pairs, we have to put in multiple bonding. So the way that we do this is, of course, hydrogen's not going to multiple bond, but the way we do is we shift a lone pair on a terminal atom into a bonding pair. So we're going to do something like this. So we're going to take, let's say, these 2 electrons here, and we're going to shift them into a bond. And this is going to give our structure. So our structure now this will now become a double bond. We still have our lone pairs there, 2 lone pairs. But now by creating this double bond, it allows oxygen to maintain its octet, right? It still has 2, 4, and 4 from the double bond, right? 8 electrons. But now carbon has its octet, right? 2 from here, and again, 4 from the double bond to give us 8. So by making that extra bond, right, that pair of electrons counts now twice, right? So we can get to the octet without using any more electrons by creating an additional bond. So that's when you want to start invoking multiple bonding, not until you need it. All right, so good structure there. So the last one I want to do right now is an example of a polyatomic ion. So while we can do structures of neutral compounds, we can also do structures of ions. So let's do a simple polyatomic ion. So this is one of our polyatomic ions, right? So this is hypochlorite ion, ClO-. Now, we don't really need to worry about what goes in the middle, of course, here because it's a diatomic. So we're just going to draw out our 2 atoms, but we do need to count up electrons. So we got 7 for the chlorine, 6 for the oxygen. Now here's where the thing with the ions come in. So we have to take that into account in our electron count. So because we have a -1 ion, that's going to add on an additional 1 electron, right? So we have an additional electron. If I had had a positive charge, I would take away an electron. And if I had a -2, I would add 2, etc. So this gives me 7 plus 6 plus 1, 14 electrons that are going to be in this structure. Now, notice, every structure I've done so far has an even number of electrons. That's important, right? Because, everything's going to be in pairs. So if you end up with an odd electron number in most of the structures you're doing, maybe you check your count. Maybe you got the wrong number, maybe you didn't account for a charge, etc. So let's go ahead and put these 14 electrons in. So we're going to make our single bond. That's going to use 2 electrons. Get me down to 12. Now I'm going to satisfy the octets. So oxygen needs 6, chlorine needs 6. So yes, I have 12. I can do that. If I look at my structure, oxygen has an octet, chlorine has an octet, so we should be good. Now, the one last thing we have to do for an ion, right, these polyatomic ions, is we always put our polyatomic ion in brackets, and we show the charge on the upper right-hand corner, and this indicates that we've drawn the structure of an ion, and this entire structure has an overall -1 charge. Right? So anytime we do a polyatomic ion, we're going to have brackets around it. We're going to have whatever the charge on that ion is outside the brackets in the upper right-hand corner. All right, so from this point, we're going to move on a little bit, and we're going to talk about a concept called resonance. Now, what resonance is it is the idea that in a Lewis structure, we cannot always account for the actual structure. So sometimes we have multiple structures that we can draw that will do the same thing. Now, we have to be careful when we talk about multiple structures. What we mean is multiple arrangements of the electrons, right? So one thing that we want to emphasize here is in resonance structure, the skeleton structure, the skeletal structure, as I can't spell here, but the skeleton structure is the same. Right? So we're not switching what's bonded to each other. Right? We get our basic structure. All we're changing is where the electrons are located. And so let's look at some examples as we go through here. Now, if we have this, we get what's called delocalizing of the electrons. And we call this concept resonance within the Lewis model. And so we'll have what we call multiple resonance structures. And this is a good thing in the sense that when a structure has delocalization, it's a stable structure, right? Delocalization helps to stabilize a structure. But one of the limitations of Lewis structures, right, is we can't show one structure here. The only way that we can convey this idea of resonance or delocalization is by drawing multiple structures. So when there is more than one Lewis structure, right, that we can change the position of electrons, right, only the position. These are where we get our resonance structures. Now, key thing, right, I'm going to say this a couple times, right, the actual molecule is what we call a hybrid of the resonance structure. So in other words, there is just one actual structure. So when we have that molecule, it exists in a certain structure, right? It doesn't have half this structure, half that structure, right? So, for example, when we draw out the Lewis structure of O3, ozone, right, you get in a situation where you have to put a multiple bond in. So you might start out with, you have to put this multiple bond in, and you put it over here on the left-hand side. Well, why did you put it on the left-hand side? You could have just as easily put it on the right-hand side. So these two structures are identical in every way except the way the electrons are distributed. So these are what we call resonance structures. And the key is, which of these is the real structure? Well, a combination of these structures is the actual structure, what we call the hybrid or the resonance hybrid. But again, the structure doesn't change, doesn't resonate between the two. It is some combination of the two structures. And again, one of the limitations of a structure is we can't draw this, right? We can't draw in Lewis theory. We have to do the two resonance structures or multiple resonance structures. It's the only way that we can convey this idea. And it's a limitation of the theory. Okay, so let's do some resonance structures. Now, I put this picture in to, again, emphasize this point, right? There is one structure, right? So let's say for ozone. Now, again, we can sort of imagine the hybrid being something like this, where the double bond isn't on the right or on the left. It's sort of shared. So each of these bonds is kind of part single, part double, somewhere in between. Right? Again, this is sort of how we can try to draw a structure of a hybrid. But the key is, this is the structure, right? Or one structure is what we have for ozone. It's kind of having dogs that are bred, right? You know, if you cross, you know, a goal of, let's say, a golden lab with a German Shepherd, right? You get some hybrid dog, but this is the dog, right? The dog isn't some days a German Shepherd, some days a golden lab, right? It is the hybrid, right? That's how it exists all the time. Same idea in molecules. There is a form of the molecule, and there's not these multiple resonance structures in reality. It's just a way that we can visualize what's going on. So let's draw one of these. So let's look at the molecule NO2. So, oh, sorry, NO2, can't forget here. Sorry, I almost forgot to draw it. NO2 minus. All right, so we're going to do the nitrite ion. So let's lay out our skeletal structure. So again, nitrogen is going to be in the center, lowest electronegativity. Oxygen is going to be on the outside. We're going to have 5 electrons from the nitrogen, 6 electrons from the oxygens. We have a -1 charge, so we're going to add 1 for the charge. And so we end up with 5 plus 12 plus 1 gives me 18 electrons. So first thing, of course, we make our single bonds. Took 4 of them. Now we start satisfying the octets of the external atoms. So we have 2 external atoms. Each oxygen needs 6. It's going to take 12. We have 12. So we go ahead and put these in, leaving me with 2. So I progress onto the center atom, the nitrogen. It has 4, right? 2 here, 2 here. So it needs 4 more. But of course, we only have 2. So we're going to go ahead and put a lone pair here. We're going to use up that last 2 electrons. But nitrogen is still without an octet. So again, just like we did in COH2, right, we're going to move a lone pair to transition to a bonding pair. Now the question is, which lone pair, right? Or from which atom, right? We can move it from here. Right? We can move, say, this one in, or we could move this one in. Right? Which one to choose? Well, you kind of just have to choose, right? So let's say I do this one. And I get a structure that looks like this. So I moved one of the lone pairs away to get this kind of structure. Now, again, there was no reason I wouldn't do it on the right. And so this is where we get resonance. Now, again, resonance, we have to draw out multiple structures. Now, before I do that, I can't forget, this is an ion, right? So I need to enclose my ion in brackets and put a negative charge there. So now I can draw the other resonance structure, which has the double bond on the other side. And so now we have our 2 resonance structures for this molecule. And again, the actual structure is some hybrid between that. But that's the idea of going through with resonance.